Hello, my people. Hope we're doing well. Let's go ahead and get started. This one actually, when I was putting this together, I didn't actually take a good look at that, and this winds up being a little bit more complicated. So we will save that one for the end. But let's go ahead and get cracking on this one right here. Now, I recognize the fact that the left-hand side is more complex than the right-hand side, but the right-hand side does give us some indication as to what we should be doing. Now, if I know that the right-hand side denominator is only in terms of cosine, then I might go ahead and think to use the Pythagorean and change sine squared into 1 minus cosine squared. That actually is going to be a really good idea because that then factors as that. And I say to myself, that looks pretty much like that. I wonder if 1 plus cosine is a factor of that numerator. Well, if it is, then what should be left over is 1 minus 4 cosine x. You don't even have to do the factoring. You can just sort of write it down like this and then do the multiplication in your head to make sure that it actually works out first. And then the outer and the inner is going to be negative 4 cosine plus 1 cosine, which is negative 3 cosine, and then negative 4 cosine. So it does. Okay? And so the thing is that oftentimes we need to factor, but so often the factorization is sort of given to us in the midst of the problem because it can't be otherwise. I hope that makes sense. I basically used kind of where I was going to identify where I needed to go using sine squared to 1 minus cosine squared. And then the factorization, I know that if 1 plus cosine evaporates, it has to cancel with a like factor in the numerator. I tested it out, and it winds up I'm right. Okay. Alrighty, let's go ahead and take a look at that one. What I have here is cosine squared minus sine squared over 1 minus tangent squared. Now, 1 minus tangent squared really isn't anything, right? Neither is, well, cosine squared minus sine squared is something. You just don't know what it is yet. But, you know, tangent squared is plus 1 is equal to secant, but this is 1 minus tangent squared. And so I have to do something with this. Well, I know that it ultimately becomes cosine squared. Okay. Well, how am I going to get there? I need to figure out a way to turn the denominator into a single term. Now, that only happens by cancel. I need to get rid of the binomial in the denominator. That either happens by using a Pythagorean to turn a binomial into a monomial, or that binomial simply disappears, right? Well, here's the thing. I notice that these have a similar structure, right? And I know that both of these second terms right here have a sine squared. So how would I turn tangent squared into sine squared? Well, I'd multiply it by cosine squared. And if I multiply it by cosine squared, I have to multiply the numerator by cosine squared. Okay? Now, in order to do this, we simply have to fight the urge to distribute the cosine squared in the numerator, despite the fact that we are distributing it in the denominator. And the reason is because the moment that we do that, those cancel, and I'm left with cosine squared x is equal to cosine squared x. Cha-ching. Okay. Now, let's go ahead and take a look at this next one. And you have a trinomial over a binomial. Everything except for that one is of the second degree. And then all of that is equal to cotangent squared. Well, I just so happen to recognize that identity right there. okay? And of course that, is obviously the first one on our strategy sheet. So sometimes a fundamental ID can be substituted at the very beginning of the problem, okay? Well, let's go ahead and see whether that actually helps us out. And I get 1 plus cotangent squared, and I get 1 plus tangent squared. Well, it just so happens that both of those are really, really helpful, right? Because 1 plus cotangent is cosecant, and 1 plus tangent squared is secant squared. Okay, well, if that's cosecant squared theta, okay, and that is secant squared theta, then isn't that 1 over sine squared theta and 1 over cosine squared theta, which amounts to cosine squared theta over sine squared theta, which of course is just cotangent squared theta. Okay, and so the key was, not being shy about testing it out. Try it out. Go ahead and plug it in. See if it gets you anywhere. And then we have a numerator and a denominator that both have straight up Pythagorean IDs. Now, once you get to here, you could actually sort of skip a step simply by multiplying, knowing that the denominator is 1 over cosine, multiply the numerator and denominator by cosine squared over cosine squared, and that would jump you straight to here. Okay? But, I mean, either way, it doesn't really matter. I wanted to basically show this to remind you that this is a complex fraction and can be handled, like all other complex fractions. Now, let's go ahead and take a look at that. Okay, so I have secant plus tangent squared, and that's equal to 1 plus sine x over 1 minus sine x. Well, I don't like the second degree on the left-hand side, but I really don't like the binomial over the binomial over here. So what do you say? We go ahead and try and turn that into a monomial denominator. And of course, the way that we've talked about doing that is by multiplying by the conjugate in order to turn that denominator into a recognizable Pythagorean ID. We get 1 plus sine x squared over 1 minus sine squared x. This over here becomes sine squared x plus 2 sine x plus 1, all of that over cosine squared x. Well, that winds up being kind of interesting, because what happens here is that becomes tangent squared x, because when I can separate that fraction and simplify. That becomes 2 tangent x secant x, and when 1 is over cosine squared, that becomes secant squared x. That looks a whole lot like that would if I were to FOIL it. And it is, okay? And so this becomes secant x plus tangent x squared, and that, of course, is identical to the left-hand side. Cha-ching. Okay? Now, I could have started on this side, but multiplying it out, I would have gotten to here. I might have gotten to here, but would I have seen these last two steps running in the other direction? And that's, it's questionable. Okay? All right, let's go ahead and take a look at this one down here at the bottom of the page. 1 minus tangent squared, quantity squared, is equal to secant to the fourth minus 4 tangent squared. Okay. Now, I recognize the fact that this is going to be of the fourth degree. This is already of the fourth degree. And one thing I remember about secant and tangent is that they both have an implied denominator of cosine. So there are probably a number of ways that I can do this. I'm looking at the right-hand side and thinking that I want to pull out a secant squared x, and that would leave me with secant squared x minus 4 sine squared x. Now, is that helpful is the next question, right? And I'm not sure that it is. On the other hand, on this other side, we could make this into tangent to the 4th x minus 2 tangent squared x plus 1. Now, which one looks preferable? Well, I also know that I don't necessarily have to treat it like this, like tangent x, okay? Both of these can be transformed. Let's go ahead and ignore these. Both of these can be turned into, if this is secant to the 4th x, I remember that tangent squared is secant squared minus 1. Okay, so that can be secant squared minus 1, which becomes secant to the 4th x minus 4 secant squared x plus 4, right? Being careful about the distribution. Well, that can factor into that. Okay, well, I also happen to remember that secant squared theta minus 1 is equal to tangent squared. But that's secant squared theta, that's secant squared minus 2. Okay, well, can't that be divided up into secant squared minus 1 minus 1? And therefore becomes tangent squared x minus 1 squared, which, as we've talked about time and time again, can be turned around into 1 minus tangent squared? It can. Okay. Well, I mean, you could have also, realizing that this secant over here is not going to change, we could have, and the thing is that we could have, I mean, there are, oh my gosh, there's tons of ways that you can do this one. This one is secant squared squared, so it could have become tangent squared x plus 1 squared. And you could have then combined it with the negative 4 and simplified it all out, and basically you would have gotten down to something akin to that, okay? But this one can be, 1 minus, well, tangent squared is secant squared x minus 1. Oh, sorry, that shouldn't be there. Squared. Well, when I simplify this and distribute, that becomes 2 minus secant squared x squared, or secant squared x minus 2 squared, which is, of course, identical to that. And so this one can be done either way. You can do it in terms of tangent, you can do it in terms of secant, but one way or the other, you're going to have to turn one into the other using the Pythagoreans. And how best to do that is really kind of up to you. Where do you see it? Do you see it here, or do you see it here? Okay? And that's kind of a dealer's choice, okay? All right, let's go over this last one right here for this particular video, and then I'll sort of bring this one to a close, and we'll jump on the next one. Actually, on second thought, we have a minute or two. Let's go ahead and back up. I want to, I've already done this one way, right? I want to do it full on in another way. So basically, this was one way. Let's do it, and I've done it sort of halfway here. Let's do it this way. I want to do it that way real quick. Okay, so I have 1 minus tangent squared x squared is equal to secant to the 4th x minus 4 tangent squared x. Now, like I said, the secant to the 4th is secant squared squared. And secant squared winds up being tangent squared plus 1. Now, if that's the case, and I FOIL this out, and basically this negative 4 tangent squared basically is going to turn this positive 2 into a negative 2. right? So whereas it did expand out from tangent squared plus 1, this negative 4 turns that positive 2 into a negative 2, and it collapses back, or factors back, probably a better way to put it, if we're going to use official terminology, back into tangent squared minus 1, which then, of course, is the same as 1 minus tangent squared x squared. Okay? So like I said, oftentimes there's one best way to do a problem, but sometimes there's tons of ways of doing it that are related, and no one way is really any more difficult than the others. Okay. Now let's go ahead and take a look at this last problem right here. Now this is actually kind of similar to one that we've done recently. Let me see if I can flip to it. Yeah. Okay. Actually, that's really, really similar. Okay. So let's go ahead and do this real quick. It isn't a bad thing to go back over this. You're going to be going over problems again and again and again that have a very similar structure to them. And that repetition is actually, while some of you may be bored by that repetition is actually advantageous. And so what we have here is 1 plus 2 cosine x plus cosine squared x, all of that over 1 minus cosine squared x. Well, if we then transform that denominator using the Pythagorean, we get sine squared x. And then if I separate the fractions, and I'm actually going to show the separation of fractions here. Remember that if you have a monomial denominator, that can become something like that, right? That's what I mean by separating the fractions. And of course, separating the fractions and then simplifying really only works if you have a monomial. And of course, multiplying by the conjugate, utilizing that logic of the difference of two squares to get to a recognizable Pythagorean, which can then be taken from a binomial to a monomial, makes that possible. And we get cosecant squared plus, well, I'm going to take this cosine and marry it to one of these sines down here. The other sine is going to become cosecant, and I get that quadratic structure. I get that basic expression in terms of a quadratic structure, and because it has a quadratic structure, it can factor like that. And there is my verification. Okay. I hope that, and the thing is that I'm not trying to march through these in any sort of like lockstep way. When there's appropriate ways to show you to do things in a alternate way, I want to stop and do that for you, because I want you to have confidence as you move forward that simply because you can't see the end doesn't mean you're going along a false path in terms of doing it. And that's great and that's comfortable. And just because, if you're doing your homework with a friend and yours winds up looking very, very different from somebody else's, that doesn't necessarily mean that you're wrong. That's why the answer key for the homework that I've posted, it says, it basically says, problems 9 through whatever, solutions will vary. It doesn't even show you any solutions. And the homework and the old worksheets that I posted that have an answer key that I have worked out, those are just one way to do it, okay? If you have any questions as to whether you have worked it out in a valid way, all you have to do is just, shoot me an email, shoot me a message on Teams, and I would be more than happy to take a look at it. Do that if you have any questions, and if you still are a little bit fuzzy on this, then tune in for video number 3. Bye.